Hey everybody, welcome back to Fastware. So today's topic, undoubtedly as you've seen from the title, it's the evil goto statement. When exploring this topic, I found one particularly interesting fact. Never trust people when they say trust me. Because they're either lying or they're mistaken, and therefore you should explore it for yourself. And this is what I want to do with you today. So most of the people have never written goto, but they just repeated like dogma that goto is evil and you basically will destroy your code. It's gonna be either unreadable or you're gonna crash it. That's not entirely true. So you see, we use pointers and raw pointers when we need to access memory. However, we not crashing our programs. We know how to use it. And goto is in a similar vein, just a tool. So a simple goto expression, if you have never written it, looks something like that. So let's say you have a function a, which takes some argument, whatever it is, right? And then in here we will do an if a equals to 10, some sort of a check, and then we'll do go to end. So let's say that this particular situation, that end is, we need to skip all that code. Now here, you either declare all your variables up front. Let's say you have some many variables you before the first go to, or better yet, you declare a scope and then you say some more code here. And then at the end, you have this end label. So this is how you define a label. And then at the end, maybe you want to do some void pointer. Here's some memory. You call some read function at some index, whatever. And then you do broadcast, if I can spell this memory. Something of that kind of a thing. And as you can see, there is really nothing to it. Obviously, C++ and C with the inlining is powerful enough, so you could basically probably put all of that code in another function. But it's good to know that there is another tool if you need to force inline a bit of code, and this is the tool to use it. Now, is it safe? Yes, it is safe, if you know how to use it well and you practiced. If it's your first time writing goto, don't put it in a production code. Practice it, understand every little bit, stare at the assembly, understand what is being generated. It's not that problematic. But now let's jump into the actual topic at hand. What I wanted to show is the realistic application of the goto. It has been implemented in pretty much every virtual machine that I know of. It tends to speed up the performance of a virtual machines, which need to basically execute instructions, so like an interpreter or something. I think both Python, Android, all of these have implemented in their core engines. I think even Lua maybe, I'm not sure yet, but you can double check. So this is the general situation that we tend to have. We have some sort of event stream. So you have add, subtract, multiply, divide, modulus, and whatever. And then normally what you would write is you have this loop through all the event data, and then you add, you subtract, you multiply, you divide, you perform the modulus operation, right? So it's just in the loop. So you look at that and it's like, there is no way to make this faster. This is like as good as it gets. But you'll be mistaken in this particular situation. There is, and this technique is called the indirect jump tables. So normally a compiler writes a jump table for you where you need to jump. But with certain extensions in GCC and Clang, I actually don't even have to pass them in. Compiler understands what I'm doing here. I can write my own jump table. So, and this is how it goes. So again, I have my events, and here is my jump table. I say that I have a void pointer jump table, so a raw address, right? And I'm saying for add label, I want to use my label, my goto label. So here's my goto label. So double ampersand takes a reference of a label and produces a void pointer which can be stored in a jump table. So, and then I do the same for subtract, multiply, divide, modulus, and the end label. Now, notice that this loop that was around my events is gone. It's no longer there. Instead, what I have is I extract my first event out of data, which is of that vector. I have a little sort of a helper lambda here called next, which just accesses the event, increments to a next event, dereferences it, and then using that event indexes into the jump table, producing a void pointer. So this function returns a void pointer. Now, here's how we use it. We say goto, dereference that void pointer into now a label, and then jump to that label. So let's say our first label is subtract. So we immediately go and jump into subtract. We perform the value and then do exactly the same step, getting a next value. So the next value might be a modulus. So and then we jump to modulus, performing that operation, go to, let's say, multiply. And we do a direct jumps from label to label rather than what a switch would do in this particular case is go read the headers again and then do the checks, what needs to be invoked, to which label you need to jump, and then continues again into the code and then does the same thing. So this particular code, as I said, jumps from the header into the target label and then back to the header to the label, while this one jumps from label to label. That's the difference. Now, as you're undoubtedly aware, I'm going to run a benchmark demonstrating the performance of that. So here it is. So we completed our switch, and then here we completed our goto. So I think we can safely ignore the tiny switches here. The performance is very much different between those, but I think it's just some inconsistencies with the branch predictor. But at the larger scales, as you can see here and here, what we tend to have is about, I'd say, 15 to 20% performance improvement. So a simple switch statement using this technique, obviously a large, and this is a caveat, which I will demonstrate in a second, a large switch statement, a large enough switch statement, can be optimized and you can gain up to 20% more performance out of it. Now, this is the caveat for GCC, and specifically for GCC, because I tested on Clang different versions and Clang doesn't do this, but GCC does something miraculous here. Assuming that we don't have this modulus operation, or divide or multiply, it doesn't matter which one, but we're reducing the size of our switch. So we remove that, we remove our modulus operation, and our jump targets as well. Right, so we completed this, and now let's try to run it one more time. So remember the numbers, so here they are above. Have a look at the difference, especially for the switch case, because the goto case is probably a little faster in some cases, but it's about the same. However, the switch case changed the performance drastically, like drastically. It's what, almost 10 or maybe 8x performance improvement. It's unbelievable. And I looked at the assembly, which I will share with you. We will go to Compiler Explorer and to try to understand what is happening. Not in great detail, but just a general overview. So let's jump to that. So here we are. This is the original example where we have all the events. And this particular switch statement, if I reveal linked code, So here it is, our switch. We jump off the label. So here's our subdivision, right? So there's probably somewhere here our multiplication as well. Where is it? So here's the modulus operation. Here's the multiplication, subtraction, and I'm guessing addition. Yeah. So the code is sort of laid out in these sort of sections of do this, then, jump to label. So the important thing is how the switch itself is. So we extract a new value to jump to, and then we jump the offset to the value. But now let's have a look what exactly happens to the switch statement if we comment out one of them, like I did in my different example. Let's look at the switch statement. This switch statement has transformed into something weird. You do comparisons and then you do different kind of jumps, and then you jump to label 144, which is here. So it does implement it in the weird way. It appears almost like an if statement. If this, then jump here, else jump there, compare something else, and then jump to another label, which is funny. So this particular pattern is weird. But I think the more interesting thing is to have a look how the label example looks like. So let's have a look at our label. So reveal linked code. And here it is. So here is our add. Here is subtract. Here's our multiply. Here is our division. And here is our modulus. So as you can see, the entire code, what needs to be executed, is linearly laid out back to front, and it basically reads the address into from the jump table into the RDX register, and then dereferencing the RDX jumps to that address. So this is how the jump table is implemented, and it's a beautiful pattern. And the larger your switch statement, the better this thing performs. So I would like to recommend, with a caveat, if you have a large kind of a event processor or something where you pool your events and then process many at the time, this is a great pattern to optimize your code and gain an additional 15 to 20% of performance, literally for free. So there is one more thing that I would like to show, a comparison. So the larger switch statement, number of nanoseconds per single instruction. So I'm using these metrics, which is just the value produced here divided by the size. So the size of the problem, right? And then we get the values here, and exactly the same for goto. And as you can see, at about this scale, we have about 4.2 nanoseconds per operation, while here we have 5 nanoseconds per operation. So again, 15% improvement, which is not bad, almost 20, but 15, let's say. Now, in the small switch example, the data looks completely different. So this, the blue is the original switch, and this sort of a if-like switch implementation that GCC does. And as you can see, at small scales of data set, which is, I think, the common case for most applications, this actually performs so much better. So don't use just because you know how to write a jump to label, indirect label access, doesn't mean that you should write it everywhere. It's a big caveat, and you need to understand and measure where it is useful and where it is not. With that, I finish my goto examples, and I would like to ask for your opinion, guys. I would like to start a series doing a longer topic. I have few in mind. One would be implementing custom memory allocators. So we would take 3, 4, or 5 episodes to basically implement different forms of memory allocators, see how they work, how they perform, compared to malloc and whatnot. So that would be an interesting topic. I like doing that sort of a thing. So if you like that, please tell me in the comments that you want to see that. Or we can do a high performance logger, which just basically does async logging. Probably an atomic logger as well. So we'll be looking at atomics while we're going to be implementing. So if you like that, please write that in the description. And obviously, if you have any other topic that you would like to see, that you would like, for instance, in that video series, that we would implement some larger software system, please let me know in the description, or sorry, in the comments, and we will, I think, vote up and down together, and then choose one and then go through it together. We'll start a new repository and work on that together, so the code will be available for you to have a look whenever you want, or even contribute, maybe create issues and comment how bad my code is. With that, I would like to thank you for watching. Please like this video and subscribe to the channel. It helps, at least it keeps my spirits up to know that people are interested to kind of see these sort of videos and understand kind of a more caveats and understand these problems in detail. And with that, have fun writing fast code. Now, thanks. Bye.